Can you see the screen?
Yes, we can see the screen.
So I'd like to present MAT, multi-fingered adaptive tactile grasping by deep reinforcement learning. And the idea here is to use closed-loop tactile control to effectively do stable grasping. These are my co-authors, Bowen Wu, Iredi Akinola, Jake Farley, and myself. This is a closed-loop grasping system that uses only tactile responses. It solves the visual occlusion problem in that when you try to do grasping with a hand, it gets in the way of a camera typically as you get closer. And if things don't work out correctly, you don't have any way to solve it visually. Further, it's robust under calibration error, which is probably the largest error you're going to get during these processes. It works with cluttered, unseen objects, so scenes that are fairly complex. And it works with multi-fingered hands with full degree of freedom poses as well. And what's important here is it's a simple add-on to a vision grasping system. So if you have a vision system you like for grasping, you can add this on to help close the loop under failure conditions. Let's start with open loop grasping. We developed a system, as many other people did, that does a very good job of open loop grasping. It's full degree of freedom, vision-based grasping and clutter. You can see it here picking up objects. It has a 92% plus success rate with cluttered, unseen objects. It uses reinforcement learning attention mechanism. It's trained. It's general across arbitrary high degree of freedom hands, and we'll show you that in a minute. And it directly uses a sim to real transfer. So you can train it in simulation and then directly transfer it to the real world. So that's great. And we've actually made it work with other systems. So we have a Stably arm and a Barrett hand here showing this effective open loop grasping. And we did the same training with the same policies on a different hand, a seed hand, and a UR5 robot, and got essentially the same high performance. So it's a very nice method, but open loop grasping almost works. Again, we just showed you the 92% success rate. It generates full degree freedom grasp poses. It works with hands with arbitrary degrees of freedom, but where is this 8%? And that's really what this workshop, I think, a little bit is about. You can see here some failures. You know, things are slippery. The fiction we talked about a minute ago with Rob's talk. You have calibration error. It's just a lot of things that are hard to disentangle when you have a failure of grasping. So it's calibration. Maybe your training network isn't good. You have sim to real transfer if you use simulation to train it. You have object pose difficulties, transparency, reflective objects, disturbances as you move the fingers. These are all effectively going to affect an open loop system. So how do we deal with this? So one thing we decided to do is to finish the last mile of the race with closed loop grasping. And here are some previous works just representative of some of the stuff that's been done in the past. And what's a little different about our stuff is that we don't limit it to things like top-down grasps, a low degree of freedom hand like a parallel jaw gripper, or a single object without clutter. We try to make it a little bit more general than that. So, how do humans do this? We all can pick things up blindfolded. And this is Bohan Wu. You can see he's doing a little testing here. He's blindfolded, and he's going to start to pick up these objects and get stable grasp of them. You can see what he does. He does a little bit of a search, and he does some closing of the fingers, and he readjusts the fingers. Sometimes he stops and just starts over again. But you can see that this is typical how a human would do this, and humans are very effective at this. So even if he's wearing a glove and his tactile sensing wasn't so good, he'd be able to do a lot of this. So this is essentially what we did with MAT, multi-finger adaptive tactile grasping. And as you can see here, some examples. This is a cluttered scene, and the robot is adjusting its grasp moving the fingers, and stably grasping these objects. This is all using tactile only, no vision. And so it clears the table very nicely using this method. So how does it do it? So we start with some cluttered, unseen objects. We've never seen these before. Okay, and we have an initial position, say from a vision system says where we might want to grasp. Here we show the tactile context. This is a Barrett hand with 96 tactile sensors. And this is just down here in the bottom left showing you the contacts. So what we do is we collect observations, and again, it's an important part, we only use binary tactile contacts. We don't have to worry about grayscales, forces. We just say, is it in contact, okay? We also have joint angles and some of the Cartesian locations of the finger contacts. And we get an action from that. And the action is to reopen the hand because we don't like the grasp. Or we lift it because we like it. Or maybe we don't want to close the fingers by a small delta. And what we want to do here is, if that's yes, then we can go ahead and do that. And you can see them in closing a little bit. And then we're going to start doing that again. And eventually we're going to get tactile contacts in the lower left, as you can see. And we again keep making these decisions about what we should do. In this case, we've collected the observations, and it doesn't look like we're doing very well. So the question is, do we want to do reopening? And if we do reopening, we can reopen all the fingers because we didn't like that grasp, and adjust it adaptively. And so what we can do is we can move the hand, okay, and adjust the rotation and try again. And now you can see it's trying a new grasp adaptively. Again, it's going to look for the small closures of the fingers, and you're going to get the tactile contacts showing up. And once you get those tactile contacts showing up again, we go through the same litany of questions. Do we lift it? And if the answer is yes, we lift the arm and effectively grasp the object. So here you can see a little closer on this object, it's getting some contacts. And let's talk about the state space of this particular reinforcement learning algorithm. We have binary tactile contacts, finger joint angles, and Cartesian tactile contact positions. That's the state we have. The binary tactile contacts, they're 96, and we take a time series of 20 time steps. And we use a threshold. So again, it's a binary contact. We don't worry about how the forces or grayscale, because most tactile sensors probably aren't going to give you that good information. And the insight from this is that it stabilizes the tactile signals. And it facilitates sim-to-real transfer, because in simulation we can effectively find contacts, but we really can't do a very good job of modeling the tactile sensor that well in simulation for a grayscale. So this is this contact is sufficient for intelligent behavior. So then we also have to look at the finger joint angles. And there are, again, 8 joints, 20 time steps. And the insights we get from that in terms of the state space is this is a heuristic for grasp stability. There are certain, obviously, combinations of angles which look good for certain kinds of grasps. And so this helps us find a space where there are good grasps and enable smart finger reopening when it's not a good grasp. We also have the tactile contact positions. They're 96, again, with time series, X, Y, Z location. And we get some insights out of this, is that it's a heuristic for contact stability. So it's, if you think of a cage grasp or where the fingers are relative to each other, this also gives you insights into this, into the network. So the action space is, again, to close the fingers by a small amount, effectively move it to try a new grasp and to lift it. So you can see here again, it's coming in to get it contacts. And for the finger closures, we have the ability to do it by a small amount, and we can change that delta. As we get closer to a good grasp, we can decide to do that. And what this is important is this simulates continuous motor control. So rather than having to do a discrete movement where you hit it or something, you just move it a little bit and you do this continuously. And it closes the sim-to-real gap because we can actually get motor control and simulation by using small discrete movements. And it closes the loop during training to see if we've actually hit it. The end effector adjustment, we just have to do whether to reopen the fingers, and if so, find a new end effector orientation. The end effector position is adjusted to the center of all the active tactile centers. So once we find some contacts, even though they're limited, we can then move to that and say maybe that's where we want to be looking. So it gives us a place to move to. And we can also change the orientation to see what happens then. And the insight here is this allows us to explore new Cartesian spaces. So when we have a failure, we can find a new way to get around it. And for lifting, we also have a ability to lift the arm to end the episode. And this is simply a smart way to terminate the episode during training as well. There are a number of optimizations in here, and if you read the paper, you can get the details, but let me just summarize what it is. You have terms of whether you want to reopen and give up on this grasp, whether you want to lift, and if not, whether to close each finger incrementally. And if you analyze what this learning algorithm has done, it does these kind of things. These are the insights it gets from us. It doesn't lift under few contacts, which makes sense. It lifts only under rich opposing contacts, which is kind of intuitive. And it doesn't close the fingers with contacts. So if you hit something that stops that finger, it regrasps under, a few grasps and closed grasps. It regrasps until good contact locations occur. And it learns new orientation conditional on new position. So this is really what the algorithm shows it's doing. Here we see the simulation and training. We have cluttered scenes as well as single object scenes. We use PyBullet. And again, because we're using just the contact, we don't have to worry about accurately modeling these tactile sensors. It's important that this only takes 8 hours to train. And the reason is there's no vision. It's just a small set of signals from tactile contacts, so it's very efficient. We use 300 plus objects, 1,000 plus random cluttered scenes, and again, because it's simulation, it's fast to train. Efficient also, because there's no GPU. We don't have a vision system. So you can see here, these are just the number of scenes that it's actually. So, experiments. We used MAT versus our open loop vision baseline, which we showed you before, which had very good performance to see if it helped. And we also did it against a tactile only baseline. And we did ablation by disabling the different parts of this algorithm, the position adjustment, the orientation adjustment, the incremental finger closing, the regrasping. And we again used the same objects as in the open loop baseline, clutter, setup, robot, everything was the same, so it made it a kind of a fair comparison. And I think you're going to see the objects in a second here. So here are the scene objects, 15 of them, and 15 of the novel objects we used in this system. So compared to our own open loop baseline, you can see the improvement both in simulation and in real world, was roughly the same. And here we have a single object seen and unseen both in simulation and real world. Here we have cluttered scenes, seen and unseen, both in simulation and real world. And you can see in the real world, we got a small improvement with single objects, but with cluttered objects, we got a much better improvement. But again, it helped to close that loop for us. And you can see in the real world with cluttered seen and unseen objects, it's still improved. But where we think this is really more important is grasp perturbation. Essentially, calibration error, as we said, was probably the most common thing we see when you have a hand-arm combination and you have low-cost sensors and actuators. You're going to have problems. So if this is the initial grasp that was generated by the open loop system, we perturbed it by 5 centimeters to see what would happen. So basically, your pixel attentive open loop grasp will fail probably, and what are you going to do? And so this is where MAT comes into play. And so here, we're going to start to see this. It failed, but now MAT has adaptively found the right thing. And here again, it's going to be a failure on the cone, but again, the adaptive tactile sensing will find a good grasp. And you can see it readjusting the hand and the finger closures and finding the right grasp. So if I just summarize these, with a real world 5 centimeter perturbation, you can see that the baseline, which is open loop, fails down to 20% versus it's still with MAT up in the 90s because we have this adaptive ability to grasp. And again, with cluttered scenes, similar performance. In simulation, we actually tried different amounts of perturbation. So at a 1 centimeter perturbation, you can see that you're doing about 15% better than the baseline. But if you get up to 2.5 centimeters, you can see that you're doing much, much worse with the closed loop, which is the orange. And the blue is, again, very consistently high all across. And 5 centimeters is what we showed you a little while ago. We did a baseline test against a tactile-only system, and we had slight improvement over that, but once we added perturbations to the systems, you can see the improvement became much greater. So this is where we think this is very good. If you have low-cost sensors and arms, you're going to have calibration error, and you can use this system to help close that up. We did ablation studies to see what each part of this reinforcement learning algorithm did to see how it improved things. These brown columns are simply the open loop system, and the blue is the MAT system. So again, you can see here with full calibration, no perturbation and everything, you have, again, the small increase, but as soon as you get to any grasp perturbation, the pixel attentive, the open loop system fails much more rapidly. But again, we have high performance with the MAT. And these are just showing you the components of the MAT, how they affect it, and if you ablate them. And again, we're not limiting ourselves to top-down grasps. You can use any kind of grasp you want, a side grasp, whatever, and it still can do adaptive ability to get the hand and get a stable grasp. So let me give you a couple of key takeaways from this. We're trying to solve the visual occlusion problem, which happens when you get to a point where the hand occludes the camera system and you can't see what's going on if there's a failure mode. Again, it's closed loop grasping using tactile only. It's robust under calibration error because it's adaptive. It works with cluttered unseen objects, multi-fingered hands with full degree of freedom poses, and importantly, it's a simple add-on to a vision grasping system. So start with the system you like for vision, and then you can add MAT as an add-on if needed. And it does a direct tactile sim-to-real transfer, which makes training very simple and fast and efficient. You don't have to use real-world objects. You can use models, and it works very well under that. So with that, I'd like to thank you, and these are my co-authors, and take any questions.
Thank you very much, Peter. Very inspiring presentation. Is there any question here? We have 2 minutes for question. Yes, Robert. Rob, please.
Hi. Yep. Hi, Peter.
Hi.
Impressive success rates, highest I can ever remember seeing for this kind of diverse object, cluttered kind of setting. Your tactile sensors, these sensors on the bared hand, are basically flat or only slightly curved, I take it. And if so, don't you have problems with edge contacts where you're not able to perceive that contact has occurred in some cases?
It's pretty clear that these are limited tactile sensors, and you do miss those edge contacts. On the other hand, what we were trying to show is that using a standard off-the-shelf kind of system, you can still do success. Now, obviously, the training system uses those tactile sensors for the feedback, and so it will train on grasps that are conducive to using those kinds of sensors. But clearly, if you had other, non-planar kind of sensors, you'd probably do better, but you could use the same system and training to improve it even more. We were just kind of impressed by how well it worked with those kinds of sensors. And I think the other takeaway is that we didn't feel we needed to do anything but have binary contacts. It really didn't need to have a forceful contact. And it's adaptive. And you can see in the video, as it starts to do a grasp, it fails sometimes, but then it is able to quickly realize that and come back and then get the right grasp.
So thank you very much, Peter. Is there any more question? Yes, we have some more question. Luca, please.
Yes, hi. I have a question regarding the action space. If I understood it correctly, you have for the finger closing three different binary actions, right?
For the finger closing, we have 3 fingers to close, and we decide whether we close each finger until contact. Okay. And then we also have an adjustment of the orientation and position of the wrist. If we don't like the contacts, we can move the wrist to the center of what the contacts we do have, and then we do a stochastic orientation reorient, and that's used to do the next round as we continue the system.
Okay, interesting. So have you ever tried continuous actions for the fingers? So not to say close by a force delta, but to directly get the finger positions in the action space? So the joint angles, I mean. Yeah,
we do. They're part of that's part of the state space. We have that.
Okay. State space. All right. Thank you.
The last question, you She, right?
Correct. Yes. Yeah. This is a very inspiring talk. So I kind of connected to Peter's talk to Rob's talk. So when you mentioned the like state space about the position, I'm wondering maybe did you use like a contact to estimate the pose of the contact? Because I think there are like 96 point contact. Maybe you can reconstruct the pose of the objects in the hand, and also maybe since you have 3 fingers, maybe we can like reconstruct the shape of the objects. If we can get that information, maybe it help to identify if it's good grasping. So my question is like, is the position from the contact? Did you also did it include the information of the pose information and the shape information of the objects? Yeah.
We have no knowledge of the object. In fact, the concept of object doesn't even exist here. All we're doing is saying, do we have tactile contacts? And you clearly, in a cluttered scene, you may have contacts from different objects, not from the same object. So the whole idea of an object per se here doesn't even apply. You made a good point, though, that you do have the ability to try to recreate the object geometry given the contacts. And that's something that might be interesting to do, which is a more kind of a model-based approach than this is just a reinforcement learning algorithm. But it might be interesting to try both and see what you could do to build a model online as well as doing this. In some sense, because we have it in the state space, the Cartesian positions of the tactile contacts, you can think of that as a model in a small sense. And I think that the algorithm actually learns some of those things because it does seem to try to find contacts that are certainly, successful, which probably ends up being a caging kind of contact, if you will. But it's a very interesting idea, and maybe we'll take a look at it.
Thank you.
So thank you very much, Peter. I think we don't have that much time. We are 20 minutes behind the schedule. If there would be more questions, we can take it to panel discussion.